Welcome, everybody, to our live stream from Morrison Planetarium. Well, not exactly from Morrison Planetarium, but definitely from the California Academy of Sciences. We are very excited to have you all join us for our tour of the universe. My name is Jackie. I am the manager of planetarium programming here at the California Academy of Sciences. And today we are going to dive into our universe. We're going to be using a planetarium software called OpenSpace, an open source planetarium software to travel through the edge of our visible universe and all the way back home. I promise I won't leave you out in space today. But we're going to go ahead and start our tour of the universe relatively close to home at the International Space Station. And the ISS is as far as humans travel into space nowadays. You can fit about 6 astronauts on it at any one time, and it is the largest thing that we have built in space so far. It's about the size of an American football field, or I like to say the California Academy of Sciences. So if you have ever walked our building from one side to the other, you have walked the length of the International Space Station. Now, as we look at the International Space Station zoomed in, hovering above our planet Earth, we can see a couple of interesting features. Towards the center, we have these kind of cylindrical areas, and those are where the humans do actually live. We have large solar panels on either side that help give it power. But we're going to go ahead and continue our journey, and we will travel very far away. We'll go ahead and zoom away from the International Space Station, and it may look as if it's getting tiny and tiny, yet there's nothing changing in the background. And that's because the International Space Station is tiny compared to our own planet Earth. Now, as we zoom away, I'm actually going to bring up a line that will represent the path of that International Space Station. And though even it's tiny, it's actually traveling very fast around our planet. In fact, astronauts are able to travel around our planet about once every 90 minutes. Now, as I mentioned, this is as far as humans do travel nowadays. However, that may change in the future. There's definitely plans to send people back to the moon and even to Mars. Now, if you ever want to look for the International Space Station, it's pretty easy. You actually just have to look up online, see when it's going to pass overhead. Right now, it looks like it's over the Atlantic Ocean. And you're going to be looking for something in the sky that looks sort of like a star, but it's moving very, very quickly. So maybe the next time you have a clear night, see if it's going to pass over your area and take a look. But let's continue our journey, and we're going to see how human influence has changed our perspective on our universe. So far, we have seen how far humans have traveled nowadays, but let's go ahead and see how far humans have traveled out into space. And to do that, we need to bring up the paths of some of the other objects in our solar system. So these bluish, purplish lines are showing and representing the paths of some of these objects, such as the Earth and even the Moon, our closest natural neighbor. Let's go ahead and focus in on the Moon. As we zoom closer to the Moon, we can talk about the fact that humans did travel out here in the 1960s and 70s. Now, it took the Apollo astronauts about 4 days to travel to the Moon. Now, even though the Moon is our closest natural neighbor, it doesn't mean that it's close in human terms. It is, after all, about 250,000 miles away from our planet Earth. And as we get farther and farther out today, we are going to go distances of millions or billions and sometimes trillions of miles. And when we get to these far distances, it doesn't make sense for us to use miles or kilometers as a measurement of distance anymore. So from here on out, I'm going to use a little bit of a different yardstick, so to speak, the speed of light, the fastest thing that we know of. Now, if we were actually traveling the speed of light, which is almost 200,000 miles per second, it would take us 1.5 seconds to get to the moon from planet Earth. So we say that the moon is 1.5 light seconds away from our planet. But let's go ahead and get a little bit closer to the surface of the moon. And as we do, we can start to see that it looks like the moon is covered with different things that have hit it, what we call impacts. It gives the illusion that the moon has been hit by asteroids, comets, and meteors more often than us here on Earth. But remember, Earth is a very big target, so we certainly get our fair share of impacts. The moon has basically zero atmosphere, so there's no weathering and no erosion. And there aren't any plate tectonics. So, because of that, nothing is erased once it's created or appears, like here on Earth. But let's go ahead and zoom a little bit further away from our moon and look at the path of the moon around our planet Earth. Now, it takes the moon about a month to travel around our planet, or I like to call it a month because it's not exactly 1 month. It's 29 and a half days. But you also might have noticed some other lines in our field of view, and that is the paths of some of the other objects in our solar system, the larger objects. We also have our closest star to us, the sun. Now, if we were traveling the speed of light, it would take us 8.5 minutes to go from Earth to the sun. So we say that the sun is 8.5 light minutes away from us. And we can also see the paths of some of the other objects in our solar system. If we start closest to the center of our solar system, the sun, then we have the paths of Mercury, Venus, Earth, and Mars, what we call our rocky planets. Then further out, we can start to see the paths of the gas giants, Jupiter and Saturn. And even further out would be what we call our icy giants, Uranus and then Neptune. And when we're this far out, I like to pause for a moment because it looks like there's a sizable gap between Mars and Jupiter. But this space is not empty. It actually holds our asteroid belt. And we can see some of it as I've brought up the individual points that represent some of the asteroids. Now, if I brought up every single point for every single asteroid in our asteroid belt, my computer would actually crash. So I tend to show about 60 to 70% of the asteroids. But while we're looking at the asteroid belt, I like to talk about one other object in our solar system. It's a little less known object, and it's in the center, or almost the center, of the asteroid belt. And I brought up its path, and it might be a little bit hard to see, but if we get a little bit closer, you can see a lightish blue color that represents the path of this object. And this is an object called Ceres. And the reason why I like to talk about Ceres is because Ceres has a very similar story to another object in our solar system that everybody should know or loves to talk about. And it has a similar category as Ceres. Ceres is called a dwarf planet, and that would be Pluto. And I've now brought up the path of Pluto's orbit, which is in that lighter green, or sorry, lighter blue color. And the reason why I like to bring up Ceres and connect it to Pluto is because they have a similar story in how they were discovered and how they are categorized. When we first found Ceres about 300 years ago, we thought it was the only thing orbiting in this area between Mars and Jupiter. So they called it a planet. But soon after, they found a lot of these small rocky objects that they started calling asteroids. So they decided that, all right, well, Ceres actually isn't a planet anymore. It's going to be an asteroid. And this is a similar story to Pluto. When we found it, we thought it was the only object orbiting out here in the outer parts of our solar system. But in the late 1990s and early 2000s, astronomers started to find some other objects. Now, mostly small, icy objects, but some of them were quite large. In fact, one was almost the same size as Pluto. And let's go ahead and bring up those objects. Quite a few now. These are what we call trans-Neptunian objects. So instead of adding a dozen or so more planets for us all to memorize, a group of astronomers, the International Astronomical Union, came together and decided we need a solid definition of what a planet is. And it has to be in these three, it has to hit these three categories. One, it needs to orbit a star. Well, Pluto and Ceres orbit a star, so check. Two, it needs to be large enough, massive enough to have its own self-gravity pull itself into a round or spherical shape. Well, both Pluto and Ceres are round, so check. And three, it needs to have cleared its path. It means it needs a relatively clear orbit. Well, Ceres goes right through the asteroid belt, and Pluto goes right through the Kuiper belt. So they don't consider it a planet. So they came up with a new definition or a new category, a dwarf planet. And so we actually have quite a few dwarf planets now in our solar system. Now, I know a lot of people were a little upset when Pluto got demoted, but I like to think of it this way. Yes, maybe Pluto got a demotion, but Ceres got a promotion. And we, like I said, we have a family of dwarf planets now out here in the outer parts of our solar system. So, might think of it as a different way of viewing our universe. And again, this is us humans making up these names to understand our universe. All right, I'm going to go ahead and turn off some of these objects because they do tend to slow down our computer software. And we have quite a bit to go. But let's go ahead and recap how far we've gone out into space. We've seen that it takes about 1.5 seconds to get to the moon if we're flying the speed of light. So we say that the moon is 1.5 light seconds away. The sun is 8.5 light minutes away. And now, if we were to go from one side of Pluto's orbit all the way to the other, it would take us 10 hours traveling the speed of light. So it's about 10 light hours across. And out here, we can check in on our human influence. We can see how far our spacecrafts have gone. I've brought up in orange the paths of some of the fastest and farthest spacecrafts. We're seeing the paths of Voyager 1, Voyager 2, Pioneer 10 and 11, all sent out in the 1970s. And more recently, we have the path of New Horizons, the spacecraft that went out to Pluto in 2015. Now, these are the fastest and farthest spacecrafts have gone, but none of them have traveled as far as light does in one day. So, to do that, we need to keep on zooming away from our own planet Earth. So, as we zoom on out, you might see a haze, and that's because we have turned down the light and glow of our own sun so we could see everything. And we're starting to see the true brightness of our own star, the sun, as well as we're seeing other stars. Now, the closest star to us, again, beyond the sun, is about 4 light years away from us. So it would take us 4 years traveling the speed of light to get to it. And even way out here, we can start to look at our human influence one last time. This this sphere, this round beach ball, is what is representing what we call our radiosphere. It's how far the first radio and television signals have gone out into space now. Now, the earliest radio signature that was strong enough to escape our own planet was sent out in the 1930s. So, this is a little over 90 light years away from us in all directions, since all radio signatures are traveling the speed of light. And we can even check in on how many planets we have found out here. Each ring is around a star that has at least one planet orbiting around it, what we call an exoplanet. And if you look carefully, there's actually some exoplanets inside that radiosphere. That means they have the potential of hearing our radio signature. So who knows? Maybe there's somebody listening to Nat King Cole. That'd be pretty neat. But let's continue to zoom away from our planet. And as we do, I want you to continue to keep an eye on that radiosphere. See how long it takes for you to maybe lose it or keep your eye on it. And now we get to leave our own galaxy and see what it might look like from far away. Now, we live in what we call a spiral galaxy. We have these spiral arms, and in the center is bright with thousands of stars. Our galaxy has about 400 billion stars in it. Now, as we are looking at our galaxy, can you still see that radiosphere? Go ahead and point towards it. You're all correct because I have no idea where you're looking or pointing. But if we take a look and you find my mouse, it's just right here, about 2/3 from the center. From our view right now, it looks like it's towards the top of our galaxy. But then again, there is no up or down. So it's just from our perspective that we're looking at the universe right now. Now, our galaxy is just one of many out here in our universe. Every dot we see now is not a star, but another galaxy with its own billions and sometimes trillions of stars. And the colors of these galaxies may make it seem like somebody accidentally spilt some cosmic skittles in the universe, but these aren't the actual colors of the galaxies. It shows us the different surveys that mapped these galaxies. But we'll continue our journey. We got quite a bit to go. And as we zoom on out, you'll start to see some interesting features in our universe. You'll start to see that galaxies clump together. into clusters. We live in a cluster of about 30 galaxies, large and small, called the local group. You also might see that our universe might look like a funny shape, like a bow tie or a butterfly. Now, unfortunately, our universe is not shaped like a butterfly, as cool as that might be. It's because of how we are mapping the universe. Our galaxy, the Milky Way, is made of gas and dust, and stars are beautiful, but that gas and dust actually blocks our view. So we can't see beyond our own galaxy. So these areas that are completely black, kind of looks like cones of blackness, are areas where we actually haven't mapped. We can't see beyond our galaxy, so we are not going to show you them because we don't know what exists there yet. But as our technology gets better and better, we're going to be able to map our universe even more. Still have a little bit to go, and we're starting to see some of the earlier objects in our universe, what we call quasars. Now, I do mean earliest because anytime we are looking out into space, the light has to travel so far and take so long to get to us. We are seeing those objects as they were in the past, not how they look today. So, for example, remember we talked about those closest stars to us, about 4 light years away from us? That's how they looked 4 years ago, not how they look today. And now we are seeing the universe as it was billions of years ago. And because of that, that actually means there's only so far we can go. There's an edge to everything that we can see. And that edge is kind of around us or in front of us. Let's go ahead and change our view so we can see some of it. And this is where those empty spaces actually comes in handy. We can see it a lot better. The orange patchiness is what we call the cosmic microwave background, or CMB. Now, if you had a radio telescope and you could see the microwave range of light, you would see this everywhere you looked. In fact, the first radio astronomers were pretty confused by this. They looked up into the sky with their telescopes and they're like, what is going on? Why are we seeing interference everywhere we look? But soon they realized it was actually something out in space they were seeing. These small fluctuations of bright and dark areas are fluctuations in temperature. And this is what happened, or our view of our universe as it was right after the Big Bang. Now, when I say right after, I mean only a few thousand years after the Big Bang. So we can actually think of this as our baby picture. But since there is an edge to everything that we can see, that means we actually can't go any further. We have to head on back home. Now, if we were actually that far out from space and actually flying the speed of light, it would take us 13.7 billion years to travel home. But thankfully, we have the magic of our planetarium software, so it should only take us about a minute. But one more thing, as we fly on back home, all of this that we have looked at so far, all these stars and galaxies and the cosmic microwave background, that's not everything in our universe. There's dark energy, this mysterious force that's causing space itself to accelerate as it expands. There's dark matter, this mysterious substance that doesn't seem to interact at all with light, but we see evidence at the edge and especially at the edge of those galaxies. And we talk about all of these things as dark energy and dark matter because, well, we're not quite sure exactly what it is. But we do know that it takes up 94% of everything that is out here. And that might make us feel a little small, like we're one tiny dot in this homogeneous universe. But I like to think of it this way. Yes, we're one tiny dot, but look at all that we have found, almost entirely by looking through telescopes. And there's a whole lot more for us to discover and a whole lot more for us to learn. As we zoom on back, we can start to see our human influence one more time, the paths of the planets, and some of the spacecrafts we have sent around. And we're sending even more spacecrafts to explore our own backyard. And that's what makes it a wonderful time in human history. We're not just able to learn about these things, but we can show you the map of the cosmos in 3 dimensions. And we're finally starting to unravel the true nature of the universe. But we're only just starting. The rest? Well, that's up to the next generation of scientists back here on planet Earth. Well, we made it back home, everybody. That third rock from the sun, the only place in all of this that we have found life so far. And that's pretty incredible to think about. So, welcome home, everybody. And thank you for joining us for our tour of the universe.